Thank you for the introduction. Thanks for having me here. So today I will talk about our work on both grounding and generation of natural language descriptions for videos and images. So yeah, let's start. So we humans communicate with each other about what we see in natural language. This is our primary way of communicating about the visual world. And of course, as we develop the intelligent agents, we would like them to be able to do the same, to communicate with us about the visual world. And this goes in both directions. So we want them, on one hand, to be able to generate descriptions of what they see. For example, given a video, to say someone looks at him and then walks away. Or given a language query as well as the visual content, to localize where precisely the human is referring to. For example, given an image and the query like this, to localize this little brown and white dog specifically in the image. Or another task, given again the visual query and the image, answer the question in natural language again. So what is the woman feeding the giraffe? And the answer is the carrot. And those are examples of the outputs of the systems that we have developed and I was involved in. So the main challenges that we have to face when we work with language and vision are as follows, in my opinion. So some of them are basically the inherent challenges of the domains themselves. So in language, we have to deal with the diversity of the language concepts and their ambiguity. And on the visual side, we have to face that doing robust visual recognition is not always easy. And then when it comes to doing joint reasoning about both modalities, frequently we face that we are not given a lot of supervision about the internal mappings which exist between these two modalities. We might have limited or no information about how to actually map the modalities to each other. So in this talk today, I will discuss the work which I have done on video description and visual grounding, and very shortly visual question answering, and how we sort of face these challenges in this task and how we address them. So let us start with the visual description, the video description part. So the task is follows. Given the video, we generate the description such as someone runs down the street and walks towards the house, for example. So there is the complex scene, there is a lot going on, and we have to generate a single sentence to describe it. So why do we care about this task? Well, one reason is for the visually impaired, it would be great to automate this process of creating captions for the visual content. We could also do a lot more with the search if you would be given an easy way to generate descriptions of the videos, for example, for YouTube. Well, and as I said, for interacting with an intelligent agent, for example. So what has been happening in this field in the past years? Basically, the first time we looked into this problem was when we introduced the TACUS multi-level dataset, which was focused on the kitchen domain, which was targeting different levels of abstraction that we can have in describing the video, from single sentence summary, like somebody's preparing a pizza, to a very detailed description of individual steps that the people are doing. So this was an interesting project, however, limited to this single cooking scenario. So we wanted to look sort of at a larger scale, and that's when we proposed the MPI movie description dataset, which consisted of 94 long movies, basically, and covered over 68,000 clips with associated descriptions. So almost in parallel, yeah?
What do you mean by clip?
So these are short clips. So it's not the entire movie that we can align with the text. We break down it to individual clips and sentences which describe those clips.
Clips corresponds to actions, shots?
Clips are basically aligned to the sentence descriptions. And I will just say where the sentences come from in the next slide.
And those 68,000 are part of those 94 movies, or you have 94 movies and 68,000?
No, these are exactly so. So we break down the, don't have a pointer, we have to break down these long videos into short clips. So they are part of this 94 movies, yes. So in parallel with our work, almost at the same time, the Montreal University collected their own similar data set, and we then joined our efforts, and we proposed the large-scale movie description challenge, which we have been running at last ICCV, and again we hold it at this ECCV. So this is now covering over 200 movies, and this is like a really big and complex data to work with. And just this year, two more groups proposed data sets to work on video description task. One is actually not the video, but short GIFs. and the other one is from Microsoft. It's the short YouTube clips. So what is the specific of this movie data set that we work with? And why do we actually work with it? So first of all, movies are complex, realistic, both for the large part, and professionally made videos. And then we also wanted to have the associated language descriptions for those. So one source of information could be to download movie scripts from the internet, for example. However, those have some limitations. They actually created before the movie was produced, so they might deviate from the movie itself. They're not always relevant. However, they're available as text, and one can just use them, and they are sort of available for free. However, the new source which we explored in our work is the audio description, which is available in many movies nowadays for the blind people as additional audio stream, which is actually created after the movie production to basically enable the visually impaired people to follow the storyline easier, to inform them what's happening. However, this is available as an audio, so we have to transcribe it. And here is some example of such audio description. She ushers Minnie into the house, swinging from a bottle of cola, so quite descriptive. Celia sinks down on a chair like a naughty child. She swigs some more Coke. So basically, those are really relevant to the story. How do we get to these descriptions? Well, we have to take the movie, then we have to extract the audio channels, both the original one and the mixed, the one which is mixed with the audio description, and then we have to basically extract the parts which contain these added descriptions, and then we transcribe them, and we do some further manual corrections and manual alignment to get really good alignments of this data.
The transcript process is automatic?
So we use professional transcription as some kind of crowdsourced method to try to get best quality that we can. So one of the really motivations to use this data is to have basically good sentences, professionally written. Yeah, so the data set is really diverse and complex and covers a large variety of scenes and actions, as you can imagine. So there are just some sneak peeks into some actions that we have. Yeah, so let us now look at what has been done for the task of movie description in the prior work. So I focus on some of the works here, and more recently there was more works appearing, and I guess they would fit in this structure which I sort of have here in mind. So I want to look at them with respect to what visual recognition modules they used and what language generation modules they used. So our initial approach was training some visual classifiers extracted directly from the text, and then predicting a single semantic representation and translating this with a statistical machine translation into the sentence. So more recent approaches make use of the CNN representations for visual recognition, and typically ImageNet pre-trained representations, and then they make use of LSTMs to translate this probabilistic predictions into sentences. So some limitations of this both lines of work are, on one hand, these visual representations are not targeted to the movie domain. They're really coming from completely different type of data, and we hope that the joint architecture will allow us to learn this mapping between the video and the sentence. One limitation of our prior work was that it was really constrained to using a single prediction from the classifiers, so it wasn't able to handle the probabilistic uncertainty of the visual recognition. What we tried to do in our work was to combine the sort of the good sides of the both worlds. So we wanted to train the classifiers on the movie data, to really specifically on this data, but then use the LSTM to translate this into descriptions. So once again, the challenges of the task are to recognize a large diversity of scenes, actions, and objects, as you can see. And the question is, how do we do this robustly in this movie setting? And then the only form of annotation that we are really given is the sentence and the clip. That's all we have. We don't have any intermediate labels or something. So all this recognition pipeline and the generation pipeline has to be guided only by these annotations in form of sentences. So how do we handle this form of annotation? These are the two questions which I think are the most important to answer. And the proposed approach is trying to address these challenges. So let's focus on the first part of the pipeline, the visual classifiers part. So we started off with the similar idea we had in our CVPR work. We have a sentence. We want to extract the labels directly from the sentence. So we used our semantic parser from our prior work, which is able to get certain word chunks from the sentences and come up with the labels as shown. And we know certain that there are nouns and verbs among those labels. However, one can notice that not all the labels are always visual. So like there are lots of abstract words discussed in movies like excitement, hesitation, which we would be really struggling to recognize with some visual recognition techniques that we sort of can handle nowadays. So what we propose here is to focus on the most visual part of these labels, sort of to extract what is really we are capable to recognize from these labels. And we did this by selecting 3 semantic groups, such as verbs, places, and objects. And one could consider other groups like maybe emotions, which are also relevant to the movie description task. And we simply filter out our labels and place them in the corresponding group, either based on their part of speech or based on some precompiled sets of objects and places. So this basically gives us lists of labels, and we are going to be working with those. So now we want to train a classifier for each of those labels. For example, so one important component here is to really address each semantic group. We have to pick the corresponding visual features really useful to solve this problem. So not just some generic feature, but really addressing individual groups specifically. And now, if you want to train a class,
Sorry to stop you. So how do you make sure that the verbs that you're selecting are visual?
In this case, we are just taking all the verbs. There is the further step which will look into that actually. Yeah, thanks for asking. So basically, to train a classifier for a certain label, the positives will certainly be coming from the space of the descriptions which mention explicitly this label. This is obvious. However, for the negatives, we could have different choices here. We could just take all other sentences and clips which simply do not mention bedroom. Or we could focus again on the sentences which mention at least one other distinct type of place, because this will ensure that we are not considering some noisy negatives, because there might be descriptions which describe the bedroom scene. However, they do not mention the word bedroom. Of course, our sentences are not exhaustively discussing everything. So it might be relevant, but not exactly mentioning this label. So we basically suggest to look into this group-specific negatives. And now, basically, we validate our hypothesis.
Sorry,
Yes?
Where do you get the annotations for the groups? Is this manually defined?
So as I said, for the verbs, we are getting them from the part of speech directly. And then for the places and objects.
No, you said you exclude based on groups for negatives.
Oh, you mean, so what I mean here is that all the sentences which directly mention certain place would fall into this group.
I see. And then you look into all those objects.
And the same for objects and the same for verbs separately.
So you're saying if your positive has the word, the person went into the bedroom,
Mhm.
you take negatives as the person went to the hospital.
Exactly, which explicitly mention a distinct location, because it might be saying he went to bed, which is actually what we don't want to consider as negative.
So what if it said the person went and sat in the bedroom? Then you would only look at, for negatives, you would explicitly look for clips which had sentences with other verbs and other places. Right?
Yes, that's right. Yeah. So, and the reasoning is happening independently for these groups. Yeah. So, we first validate this hypothesis. Our strong baseline is just using all the labels that we have extracted with the parser without any filtering, and use the strong feature, which is just a combination of all the features. And what we report here is the final performance of the sentences generated in terms of the Meteor score. So basically using all the labels, treating them all equally gives us 7.24. And then there are two situations here, and we consider basically all negative versus these negatives in the group. We clearly see that we have to look into negatives within the group, and this gives us a boost with respect to the basically all negatives, and also with respect to using these all labels, treating them equally. So we basically confirm both things. So I guess I skipped this information, what you were asking, but we do filter out. We have one more step of filtering the classifiers, which we consider as noisy, by looking at their ROC values. And if the ROC values are below a certain threshold, we consider that this concept wasn't reliably recognized, and we further filter out to have even less labels by still improving the score. Somehow I missed that point here. Anyways, so with that in mind,
The metric that you're using,
Okay, are you familiar with the metric?
Yeah.
Okay, so this is this harmonic mean of precision recall of word overlap. So we're looking at different word overlaps. The maximum, to see the maximum, we would need to know what is the kind of best result we could generate. So one cannot really say. That would be probably 100%. So one could say that the results we're having here is not very high because the data is quite hard. So for comparison, on YouTube dataset, which is much smaller and simpler, we are getting numbers around 20 meteor score. So just to get an idea. So this is not a very high result. This is still the preliminary result, I would say, for this data. Yes, so with these classifiers that we have trained, we basically extract the representations for our clip, and we concatenate them together, and we use this as input into our LSTM. Now, I guess everybody is familiar with LSTMs. So in our implementation, one detail is that we feed in the same visual input at every time step. So we repeat it until we get to the end of sentence. And some more details and things that we found, basically, as we started playing with LSTMs, was that actually the dropout plays an important role. And we experimented with different dropout placements, and we found that applying dropout right after the LSTMs is actually the most important one. So what dropout does is really helps us to not overfit the training data. The descriptions become less noisy and slightly more, maybe less diverse, but also more correct at the same time. So another aspect is, yes?
Video input for all these stuff was the same video, or was it different?
So we are talking about the same clip, and we're describing it, yes, at multiple steps, yeah. Another thing we played with is different random initializations and ensembling them together, and this was also, not too surprisingly, giving us quite a boost here. And finally, basically, what does this sum up on the test set? So we compare to prior works here. Again, in terms of meteor score, we are clearly improving over both prior works. And we also do human evaluation just to see how humans would feel about these generated descriptions. So humans are getting 3 sentences, and they have to rank them from 1 to 3, where 1 is best and 3 is worse. So basically, what we are seeing here in terms of correctness, so how correct the sentence is with respect to the video, our method is best. Also in terms of relevance, which means that are we describing the most important parts of the video? It's also best. However, in grammar, it is actually second best in this case. And also on the MVAT data set, we are getting similar.
What is the reason for that?
Sorry?
Grammar,
For grammar?
Yeah.
So as I will show in the next evaluation, our descriptions are much more diverse, and I guess they're maybe a bit noisier and longer than descriptions from the other system, which are more concise and therefore more sort of grammatically correct, which just makes them more correct in general. So we look at one aspect here, such as vocabulary size, for example. So this is quite striking because all the methods fall far below the actual vocabulary size of the test set. So we are not generating a lot of diverse information here. We are still able to improve quite a bit over the prior work, but it feels that, of course, in our method, we explicitly forced ourselves into the most visual, sort of most recognizable parts of the video, and we are able to get the verbs and objects in places that other systems cannot ever generate. They really seem to be not diverse enough.
So you will only be able to generate words that you've seen in your training set, right?
That is always the case, yes.
So do you know what the overlap in the vocabulary between your train and test is?
Yeah, that's a good question. I guess it's pretty reasonable. So the split is quite uniform, but I would not be able to tell you what exactly the ratio is.
And you have in your entire data set about 200 videos and
So this is done, this evaluation is done on the dataset with 94 movies.
so about, let's say, 94 videos and about, you said, 100,000 clips or so. So when you did train and test, did you allow clips from one video to be in both train and test?
So movies are disjoint. The training, validation, and test sets are disjoint.
I see. And do you have any sort of, when you randomly put stuff in train and test, do you ensure that like action genre is in both train and test?
So when we split the data, we tried to make it as uniform as we could. So really try to make the diverse genres on all 3 splits, yes. So we have Harry Potter movies in all three data splits, but they're all disjoint. Okay, so let's look at some qualitative examples. So we compared the two approaches with our approach, and we show errors in red. And I hope you can see it. Someone falls to the ground, while the others two actually say some incorrect descriptions. In this case, someone sits in the living room and sits on the TV. You might notice that the reference is really long. It's come from the movie script, so it mentions a lot of stuff. Someone is in the newspaper, then leaps up on the floor, impressively recognizing the newspaper, and makes some kind of minor error in the end. Someone is in a white dress, smiling with the smile and white hair. Sort of relevant. And some failures can be, we fail to recognize, for example, the scene in this case, well, we get the action right. So basically, to summarize this part, we defined these three challenges on the language side, on the visual side, and on the combination of both. So how do we address them? First of all, to address this limited kind of knowledge about the mapping between the two, we use these semantic groups of labels to really extract the most relevant information from the annotations that we have, and then we train the classifiers for these individual groups, and we make sure that we discard the noisy negatives, and then we provide the scores into the LSTMs, and we show that the diversity of the descriptions we are getting is better than from the prior work, which we attribute to this basically targeted classifiers that we have learned on the data. So if there are no questions to this part, I would move to the next part, to the grounding. Okay, so let's move on. The visual grounding task. So yeah, I was interested in this task just recently, and the task is given a phrase, a natural language expression, like the two girls in hats in the middle, and an image to localize this in the image, with the bounding box, for example. So how does that relate to the familiar object detection task? For example, we could have a person detector which would show us all the people in this image. We could maybe have a head detector, but when we're given the query, the two girls in hats in the middle, we really have to understand the language to locate this phrase in the image. So we call this a visual grounding task. So some useful applications could be, again, interacting with the robot. It could be providing support for other tasks like captioning or VQA, and it could help us with resolving co-references in the language part by relating it to the visual world. So at test time, we are really given just a phrase and an image, and our goal is to predict this bounding box. However, at training time, we might have different supervision available. So in the most complete case, we are given an images with all the phrases provided localization for them. So this would be the most supervised setting, and quite expensive though. On the other hand side, basically we could have an image with the phrases provided without any localization information. This is considered as unsupervised setting. And then we can have a semi-supervised scenario in between, where for some part of the data we are given localization, and for the rest we are not given it. So in particular, we are interested in these two regimes on the left, the unsupervised and the semi-supervised, because providing such visual grounding annotation in forms of bounding boxes for all possible phrases clearly isn't feasible, but collecting such annotation is much cheaper. So in the following, I would basically illustrate these two modes with these visualizations. Okay, so what has been done with the prior work with respect to this task? So most prior work has focused on the fully supervised scenario and really explored fully annotated data sets. There was some work exploring the unsupervised setting in the latent way by matching the fragments in the language and in the image. However, never explicitly evaluating the result in terms of the visual grounding quality. So, and to my knowledge, there was no work which tried to operate in this semi-supervised scenario. So this work really places itself in all three supervision modes. And the main result of our work basically is that across the board, in all three regimes, we are getting improvement over prior work. So let us dive into the approach part. Yes?
The problem with the problem formulation. Imagine a picture of a person throwing a frisbee.
Okay.
The statement is throwing a frisbee. And imagine that the person is here, the frisbee in the middle of the air, and there might be another person somewhere else. What is the bounding box for throwing a frisbee?
Well, so I guess for that case, the person throwing would be the localization. But
the statement is throwing a person throwing a frisbee.
the matter of, it might be the entire scene then. It might be really the entire scene because basically, yeah, in this
But
case.
you see my point. Basically, it's not as, again, object detection is ill-defined by itself. But this grounding task is making it just even harder.
Well, I believe that if you're given a complex scene where there are multiple people and some of them are throwing frisbees and others are playing football and it's all happening in the same scene, and then the query is people playing frisbee, then we have to localize the image region relevant to this part, yes, and not the rest. So that would be basically if your entire image is just people playing frisbee, then your entire image is the result, which happens in practice. So some queries, for example, say the street, and then the output is really the entire scene.
Sure, but you end up with a box where 2% of the pixels within that box corresponds to the thing and the rest are.
Well, I guess that's what we have to deal with such abstract queries. But I still think that in many cases, referring expressions make a lot of sense. Yes, we have to find specific region in the image.
So in referring expressions, it's better defined task.
Yeah.
The issue that I have is people putting bounding boxes for verbs.
Okay, I see. So I guess we actually, the data we are working with is on one hand using noun phrases and on the other hand referring expressions. So the verbs haven't been explicitly addressed, I guess. That would be interesting also to look at. Yeah. Yeah. Yes.
About the distinction between unsupervised and weakly supervised, so you call your segment unsupervised?
So,
is it weakly supervised or unsupervised?
So just the matter of definitions in this talk, it's going to be called unsupervised. Maybe in some object detection works, when the information about the label is present but no bounding box is present, it's called weakly supervised, I believe. But just in this work, it's going to be called unsupervised. Just, yeah, definition. So, yes, so again, the input and the output is as follows. So how do we get from there to there? Okay, so let's start with first the high-level picture, what is going on in this approach. The approach is called Groundert, grounding by reconstruction. So we start with generating object proposals in the image, and jointly each of these regions and the query form the input into the attention mechanism, and they basically give us attention weights for every region. Now, these attention weights are directly used to get the highest, basically the highest attended region is the correct grounding. That's going to be happening at test time. That's what we're trying to learn. So how do we learn this attention mechanism? Now remember, we have different types of settings with the supervision. So if we are given all the supervision, we basically know which one is the correct region. So we can directly apply some attention loss to penalize the incorrect attention. That is clear. So what if we don't have any localization supervision? Then we come up with the simple intuition, in fact, that if we have attended to a certain region, we should be able to reconstruct our query phrase just looking at this region. So if we are able to say a small boy by looking at this region, that was the right region to look at. And of course, if we are saying a white dog, it was incorrect region to look at. So we can just optimize the whole thing in the unsupervised fashion just by looking at this reconstruction loss. That is the idea, and then,
just to
yeah.
really understand, so the input would be a phrase
And an image.
And then you look all boxes.
Correct.
And then you do the attention or dot product. And
Correct.
Then
Correct. Yes, and yeah, and if we have some supervision available and for the rest of the data not available, we can combine both losses and benefit from both of them. So that means that we will have attention loss only for part of the data, but reconstruction loss for all data. Yes?
So when people do attention with EQA, for instance,
Yeah.
they would break down the image into
Spatial regions.
So let's say 8 by 8.
Mm-hmm.
You just say, which part is the attention on.
Yeah.
In your case, your parameter space is much higher because you want to get the exact location of the box, width, and height. So
Okay.
the number of attention regions is very high.
I'm looking at this object proposals only. So we are actually in practice dealing with 100 proposal regions. So the attention goes over 100 regions.
So you always assume that you have 100 proposals?
Yes.
I see.
Yes. So it's like a selection task here. Yeah. It's not a sliding window approach.
So, but when attention is usually, okay, I'll let you go.
Good. Yeah, hopefully it makes maybe clear. Okay, so that is the high-level architecture, and now we can look into detailed implementation of what is going on here. Yeah, so on the language side, we have the standard steps. Oh, yes, sorry.
Just a quick question. So here are you assuming that each object has a different bounding box? Like, do you take that into account to say that each word in an image should map to different bounding boxes?
So
a small boy and a dog wouldn't be the same bounding box.
well, that is intuitively what we assume, but we do not enforce it actually in any way in this architecture. This could be done by taking into account that there are multiple regions, and at training time actually making sure that we focus on different regions. This is not happening in this case. Yes, so I have no question. So so we have the hot vector encoding, the word embedding.
I'm sorry.
Yes.
So is like most of them you have only one bounding box to attend, or you can have multiple bounding box to attend?
So what we're going to do, we're going to take one with the highest attention. That is the setting we're working in. The attention can tell us actually that there are two, maybe, which are both kind of highly weighted, but one will still be the maximum. There is the, yeah, you will see now. So there is the standard word embedding LSTM, and then we tile this representation as many times as we have our region proposals, so say 100. Now every proposal is basically described with the CNN feature, and then the attention mechanism in the middle is basically nothing surprising. It's the two-layered perceptron, and then there is the softmax to get the final alpha weights. And yeah, as I said, the highest weight gives us the correct grounding. Now, in the supervised case, the attention loss is basically a cross-entropy loss, which is telling us what is the log probability of the correct attention to be predicted, the correct index J ground truths to be predicted given the alphas. And then in the unsupervised case, so the reconstruction is happening as follows. We have the weighted sum, which goes over our visual inputs and the attention weights. So in fact, this is not a hard attention. It's not just picking one region. It's a soft attention. And the predicted representation is then going through further one more embedding, and then into LSTM, which is then generating basically our reconstruction. So, and then we compute again the cross-entropy loss of how likely our query phrase Q to be generated given the visual input that the LSTM has received. And the semi-supervised setting is essentially, yes, the combination of both. Yeah.
What is the cross-entropy for reconstruction loss? Because what if it says a small man?
So
Is it a different category? Do you assume fixed category?
it's a standard evaluation, basically loss, which you do in image captioning, for example. You are, for every word in the ground truth, you're looking at the softmax probabilities of the words which you would say for this time step, and then you compute basically your loss.
Oh, so at each time step you have the cross-entropy loss, and then you're just summing up all time steps?
So in fact, what happens is that you do the complete phrase encoding first, and then the complete phrase decoding, and the loss is in the end, actually, of the pipeline. And this entire thing is end-to-end. So, and one important, I would say, component is that the phrase is really presented as one vector, which captures the information from the entire phrase, basically. So yeah, this is it. So if there are no questions, we'll look at some results. Okay, so we evaluate on two data sets. So one is the Flickr 30K entities, which basically took the Flickr 30K, which consisted of images with captions, and augmented every noun phrase with the bounding box. So that's the answer to your question. This is just noun phrases in this case. Yeah, the experimental setup is we take 100 proposals, we take faster CNN features. So the accuracy is going to be reporting are actually the percentage of the phrases where the intersection of a union between the predicted region and the ground truth region is above 0.5. So like you can think about it as a recall. Now, the results are shown on this following plot. So the x-axis is the amount of supervision. So the 0 basically means unsupervised. The 100 is fully supervised, and everything in between we can have semi-supervised setting, and the accuracy along the y-axis. So in the unsupervised case, we compare to kind of a modification of the deep fragments. We tried to get some performance out of it, and it wasn't fully trivial because deep fragments create certain fragments from the sentences and images. So we tried to do the best case study to match these fragments to the actual ground truth phrases and then compute the best sort of intersection of a union, and that's what we got. Now, on the supervised side, there is more work going on, and then finally, our semi-supervised result is in the middle. So what do we want to notice on this plot? One thing, without any localization information at all, our method is already actually improving over some fully supervised prior works. Then, with the very little annotations available, it has a significant boost, and it starts to basically, okay, that's what's going on. It really understands where it has to be going, and it really gets almost state-of-the-art result. And it keeps improving, and in fact, the semi-supervised setting eventually is better than the fully supervised one, which is because the fully supervised is only having access to an attention loss, while the semi-supervised is having access to both losses, and the reconstruction loss gives us useful information about other regions which could be basically helping to understand our grounding task. So, and the improvement with respect to the best prior work is 4.5%. Yes?
Is DSPE is Julia's work? Or?
That is the work from Svetlana Lazebnik, I believe.
The other question I have is that on this side of your axis, I would have thought you were going to show us some MIL baselines. This is just shouting for MIL, right?
Well, deep fragments, I believe, in this formulation was MIL.
But that's a weird kind of MIL. So
Well, the objective was to optimize for retrieval of images given complete sentence descriptions, and latently, it's inferring the mapping between the fragments of the image and the...
But it had to solve the decomposition of sentences. But the MIL, the based on MIL, that probably is not going to even work close to this. That I had in mind was break down to words and do standard MIL on it.
And by breaking down to words...
Can you go back to the previous slide that you had?
How much previous?
The one that basically showed the model.
The architecture, yes.
Yeah. So here, if you just basically get the argmax, and then instead of argmax, have like just the maximum score, because we just want to know that there is a matching between this query and the image, all the bounding boxes, and then we just optimize for having a maximum value from a pair of like multiple like boxes with a sentence, and just backward for the maximum value, just to maximize the matching, and then like have it like basically in the hidden layer you have the matching. So that would create a simple MIL.
I see what you mean. Yeah, that's an interesting... I would need to think. I mean, what I can say in practice that training the unsupervised network, it was not easy, so it took us some time to get it to work. So I am a little skeptical about the variant with the max, but that's interesting to try. Another thought we had later that what we are sort of aiming for is to get the best intersection of a union, in fact, which is never present in this architecture. So one could actually look, I mean, for given some supervision, one could also look at this intersection of a union, for example, to see how good we are doing. We are not looking at that. But yeah, those are, I guess, reasonable things to think of. And yes, so, okay, so this message is basically that little supervision basically gives us big improvement and is essentially better than fully supervised. So the second data set we look at is this referring game data set, which has a slightly different focus. It has some pointed regions in the image, and the expressions have to disambiguate this region from all other regions. So the similar setting, in this case, and here we used the feature which also includes spatial information from the prior work, because many of these expressions actually are about left, right, for example, top, bottom. So the results are very similar. So the data set is more difficult than the Flickr one. It's also smaller. And The expressions are a bit harder, I would say. However, still, with not so much annotations, we are doing already comparable to prior fully supervised method. And then we have the same tendency. And here the improvement between the semi-supervised and fully supervised is even stronger, I guess, because we are sort of providing our method with more training data, in fact. Sort of, there's more to learn from the surrounding regions, for example. And the relative improvement from the prior work is, in this case, even more significant. So let us look at some qualitative results. So what is basically the quality gap between the unsupervised and the fully supervised? Of course, there is a big gap. But what we notice is that many things the unsupervised system is getting right. So like the woman and the bicycle, and then the pavement is incorrect, and then it's being improved in the supervised scenario. So there is many meaningful things, but also there are difficulties. So another comparison, the prior work, which is fully supervised, and our semi-supervised setting with only 3% of annotations in this case. And yeah, so we can see that for a man, we are getting an improvement. And so for the brown vest and even for the dog, we are getting better localization than the fully supervised prior work. So now if you look at the referred game, so this is the type of data which there is. And here I show the predictions in red and the correct region in green. So the person in blue is correctly localized. So we kind of understood what blue means in this case. And picture to the left on the wall is basically showing that we can understand the spatial information. However, in this example, where we fail, the white horse right of brown horse in the middle, we are actually getting the brown horse in the middle, which I believe is because the language model gets confused, and also there is no knowledge about the relations between different objects which are present in the scene, which would be very natural to incorporate in this model to deal with such basically expressions. So to sum up this part, to address these challenges that we are present in this task, we are proposing the unsupervised approach with the reconstruction loss, and the semi-supervised approach, which can exploit little annotation. And then, so in terms of improvements on the visual recognition part, I think it's an interesting thing to notice that the typical sort of fully supervised pipeline can be actually improved with this reconstruction kind of additional loss, which provides us more information about our objective. And yeah, so to handle the language diversity here, we encode the complete phrase with the LSTM as a single representation. So this sums up this part. And if there are any questions, I take them, or we move to the next part. So the last part will be slightly more high level, because I was afraid that there will be not so much time for that. So, okay, I will do my best now to deal with the slides that I have. So the visual question answering. Okay, so we're given an image, and we're given the question, and we have to predict the answer. So the generation of the answer can be seen as a classification task. For example, we have to select one of the 3,000 most frequent answers. Okay, so what is happening in this middle? How do we combine the language feature with the visual feature? What has been done in the prior work, including our grounding work, in a similar sense? We concatenate the features. People have done element-wise products, so simple operations like that. The intuition that we bring in this work is that it's important that two vectors interact, of course, and as much as possible. So like ideally all the elements can interact, that we get all the different relations between them, and the multiplicative interactions would be desirable. So the ideal thing would be an outer product. However, an outer product brings us to a quite increased dimensionality situation, so it's hard to deal with in practice. So what we want to do, we want to approximate the outer product by using the basically count sketch projections. So what this figure shows us, that if we do two random projections on the inputs, and we use the fact that the random projection of their outer product is actually equal to the convolution of two random projections, we can effectively compute the following. So given two random projections of the CNN and of the visual input, basically to compute the convolution between the two, we go to a frequency domain, and there we simply do element-wise multiplication, and then we go back to our initial domain, and we obtain our approximation of the outer product. this is to tell the long story short. And yeah, so this basically is effective to compute and not as high in terms of parameters as the outer product, and gives us a good approximation, as has been shown in the prior works. So ablation studies, which we do with respect to concatenation, element-wise product, and different variations, so like integrating more fully connected layers to increase the number of parameters, they all show that this multimodal compact bilinear pooling is still doing best. So definitely it is capturing these interactions in a better way than these other versions. And one interesting ablation is to see how much are we losing with respect to the real outer product. So we have here an experiment with lower dimensionality inputs, just to be able to compute it. And we see that actually we are not losing, we're actually even slightly better. So, but in fact, I mean, it means that this approximation is quite good with respect to the initial outer product.
Is this the biggest outer product you could do?
So, yeah, I believe in terms of memory that was a limitation, yeah. So it's not as good, of course, as the best result that we're getting here, but yeah, just as a kind of ablation study. And okay, so to address the VQA task, we propose here an architecture which is based on the attention mechanism again. So sort of on the high level, it uses the compact bilinear first to combine the initial inputs and predict the attention. And then the predicted attention visual feature is used again to combine with the language input with another multimodal compact bilinear. And this is then finally being used to predict the answer of the question. So yeah, we can look in some detail into this network. I don't know, in terms of time, I think we should be kind of...
We should wrap it up sometime soon.
Okay, yeah, it is getting there. So yeah, so basically, the important things we found is that actually using this MCB for attention prediction was helping us a lot in terms of making attention mechanism work. And yeah, this won the VQA challenge on the real open-ended task. Okay, so we also showed this, that for the grounding task, the same holds. We can get improvements in terms of grounding performance on 2 data sets that we looked at, and we get better than our best previous fully supervised result. So this seems to be really general for different language vision problems. So let me conclude this talk. So I was talking about the movie description task, where we proposed this large-scale data set, which is quite challenging and very exciting to really get the improvement on this data. And one challenge we addressed was the sentence annotations. So we showed how we can train robust classifiers by having this semantic groups of labels, verbs, places, and objects. And this can be actually scaled to having other groups as well. So on the visual grounding task, we showed that the approach we propose can work with none or very little localization supervision, which is achieved by this reconstruction loss that we integrated. And yeah, for the visual question answering, we basically showed the advantage of exploiting different pooling strategies as opposed to standard concatenation or element-wise product. In particular, the multimodal compact bilinear shows a big boost for this task as well as for the grounding task. Yes, and this won the challenge. So just to outline some future directions I would like to work on, and some of them are actually work in progress, is on the description task. I think our data allows us to study multi-sentence description because we have many continuous clips and continuous descriptions in the data set. So we have done this with the kitchen data in the past, where we had much more structured kind of data, which was a lot easier. So on the movie data, it's a bit harder, of course, to predict what happens next, given, for example, what we have seen before. What could be helpful is the modalities which are present in our data, like audio or dialogue, which is essentially available for us for free, so we could make use of that data. For the visual grounding, as I said, would be good to, at training time, inform our model that there are multiple phrases present in the scene, that we can actually learn to not attend to the same region, but rather diversify our attention, and to address certain queries, we really need to model spatial relations between these different objects in the scene. And one project, which is an ongoing work, is that I like this idea that we can use some of the grounding knowledge that we have learned in this project for the movie description task. In particular, we could try to learn the character mapping, so basically the mapping between the visual appearance of people in the movies and their names in text in a weakly supervised manner by, for example, using Groundert. So that's some project which is going on. And with that, I would like to thank you for your attention and also thank my co-authors who helped a lot, of course, on all these projects. And yes, I take any other questions if there are remaining questions. So thank you.